Hello everyone, this is the third video related to Beckmann reaction, and in this video the topic is Beckmann fragmentation, which is also sometimes called abnormal Beckmann reaction. It will be easier for you if you watch the first two videos and then you watch this one. I will give the link for the first two videos in the description box. So let's start Beckmann fragmentation. So now you can see normal Beckmann reaction where we have this type of moiety where R and R prime may be connected. If it is connected, it is cyclic, and in that case it will be lactam cyclic amide, and if it is not connected then it will be amide, and here the intermediate is nitrogen ion. But suppose if this type of mechanism is not happening, something else is happening. So what is this? If this R and C, this bond is disconnected completely and this part is removed in the form of leaving group, then we will call it Beckmann fragmentation. Now after Beckmann fragmentation, suppose there is a recombination by attack of this nitrogen. So in that case Rn bond is again formed. Okay, so it will be back to the normal Beckmann product. So that is written here, normal Beckmann product amide. So this is Beckmann fragmentation plus recombination, and that I have discussed in the first video. You can watch that, but it is not Beckmann fragmentation because ultimately you are getting Beckmann product. Okay, so if from this, after this fragmentation, no recombination is happening by the attack of nitrogen, but instead there is a attack by any nucleophile which is present in the medium. In that case you can see there is no formation of Rn bond and there is a formation of bond between the nucleophile and the R. Now this nucleophile can come from the reagent reaction condition, it may vary. So this is one of the possibility after Beckmann fragmentation. Another possibility is if this R plus, there is a removal of H plus from this R plus portion, and then there is a formation of alkene CC double bond. So these are the fate of this R plus after Beckmann fragmentation. Now the important question arises, when Beckmann fragmentation will occur? So fragmentation is likely if nitrogen, oxygen, sulfur, this type of heteroatom is present in the oxymino group. So here you can see oxymino group. So you can compare this molecule with this one. Obviously R and R prime, these two are not connected here. So here you can see XC is attached to C double bond N. So this is our C double bond N, and if in this R you can imagine there is a heteroatom attached to carbon which can be nitrogen, oxygen, sulfur. So it can this lone pair can be pushed in the right hand side. There will be X double bond C, and in this case this CC bond is broken and this is a leaving group as it is. So this is one of the possibility where Beckmann fragmentation can occur. Then it can also occur when the alpha carbon can support cationic character. Suppose after the RC bond cleavage, if R plus carbocation is very stable, then cationic character is supported. So in that case also Beckmann fragmentation can occur. And another possibility is if there is a ring strain relief, something like this is happening, that can also be the driving force for Beckmann fragmentation. Now we will see examples one by one. Here we have the first example, NOH. So whether this side or this side is anti to OH, that is not understood from this picture. So if this type of situation arises, what you will do, when you will make the leaving group, you have to consider that portion for the, that is you will break it where it is more stable, because here we are not migrating, that is anti-migration, that is not happening because it is Beckmann fragmentation. So you just have to make positive charge, and here you can see it is stable here. So after removal of HCl from POCl3, that is this H and one of the Cl, you will get this type of leaving group. Now if this CC bond is broken, the carbocation will be formed here which is very stable, right? So after removal of this leaving group, so what is happening here, this CC bond is broken, CN triple bond is formed and NO bond is formed. So here alpha carbon can support this cationic character. So this is the alpha carbon which can support the cationic character. So that is the driving force, and ultimately there will be attack by this nucleophile. So that is why it is written, it is the fragmentation, and after fragmentation the fate of this carbocation is there is a nucleophilic attack from Cl minus. Okay, so this Cl minus can come from this PO this leaving group. Okay, so it can also take H. So there will be OH formation or this type of double bond formation, and Cl is removed. Or this O minus can capture this H and Cl will be generated from there. So ultimately in this way nucleophile can attack this positive charge, and we are getting this type of final product. Next example, here we will see fragmentation. Again nucleophilic attack by Cl minus. Here our reagent is PCl5. So first this OH that will be converted to a good leaving group like this, and one of the Cl is removed in this process. So Cl minus. Now if you see, we can't understand what is this R. So we will make positive charge at this carbon. So because after this CC bond cleavage, the positive charge that will be generated, that will be very stable. So here also we can say that the alpha carbon can support the cationic character. So what is happening here? This CC bond can be broken. There will be CN triple bond and negative charge over this oxygen. So from this portion you will get RCN and then PH2CH plus, and ultimately this PH2Cl plus that will be attacked by this nucleophile Cl minus, and ultimately we will get this type of final product. Okay. Next, in presence of H2SO4, first this OH will be converted to a good leaving group. So after the formation of good leaving group, which is water molecule will be removed minus H2O. Now you can see positive charge after the CC bond fragmentation. This positive charge is very stable. Now the same molecule, carbocation, you have to draw in this way, so that ultimately we can get aromatic electrophilic substitution. So what will happen? This double bond, it will attack here. It is ideally situated if you draw the molecule in this way. And finally there will be positive charge generated at this carbon. So finally there will be aromatization and we will get the aromatic ring back. So this total what is happening here? First fragmentation and then aromatic electrophilic substitution. So this is very interesting example. After fragmentation, this type of attack, nucleophilic attack by the CC double bond, that is pi electron, which is present in the aromatic ring. This type of incident can also happen. Next we have example 4. In presence of SOCl2, first this OH will be converted to a good leaving group, and there will be HCl removal. It will be converted to a good leaving group. And next this OH, this OH is available mode. It is in statically hindered position. So that is why this OH will be converted to OSOCl, and then there will be fragmentation. So if this CC bond is broken, see, if this CC bond is broken, positive charge is generated at this carbon, which is stabilized by this oxygen atom. So this CC bond will be broken. There will be CN triple bond formation and nitrogen oxygen bond broken. SO double bond is formed. That means SO2 will be removed from this portion, and ultimately there is also generation of Cl minus. So SO2 is removed, Cl minus is removed, and this carbocation that is stabilized by this oxygen. Now positive charge is over oxygen, and finally there will be removal of this H plus. So we are getting finally this type of carbonyl group is formed. Now we have a sulfur atom present, and here this sulfur atom will promote fragmentation. But how? First, in presence of H plus, this OH will be converted to a good leaving group, OH2 plus. Now this sulfur, it can attack at this carbon. There will be CS bond formation. This CC bond will be broken. There will be CN triple bond, and this OH2 will be removed. So finally, after water removal and also this type of CS bond formation, CC bond cleavage and CN bond formation. So here you will get a CN, and here we have total 4 CH2. So you can also put numbers so that you don't make any mistake. And finally, this nitrogen lone pair, it will attack here. So this CS bond, that is sulfur, will be neutral again, and you will get this type of final product. So here sulfur is promoting fragmentation, though it is present at a long distance, and it is possible in this case. Next example, in presence of SOCl2, first we will convert this OH to a good leaving group. So after formation of this good leaving group, OSOCl, and obviously there is minus HCl. Now you will see, if there is heteroatom present and it can promote this type of NC double bond formation, and finally this CC bond will be broken, and there will be CN triple bond formation and NO bond will also be broken. So from this part we will get RCN, and from this part we will get R2N plus double bond CH2. So total how many fragments you are getting? R2N plus double bond CH2, RCN, SO2, because here there will be a double bond, so this portion you will get SO2, and there is a Cl minus, and finally after hydrolysis we will get R2N. So if you look at the starting material, from this portion we are getting R2NH, then from this portion we are getting from this CH2 we are getting formaldehyde, from this part we are getting RCN, and this is converted to living group. And the last example, this is very famous example which is taken from Clayden. Probably it is already you have seen it. So first, in presence of CH3COCl, this OH will be converted to a very good living group. And as this carbon, it can carry positive charge in a very, it can support the positive charge, right? So that is why fragmentation is possible. So after conversion to a good living group from OH to OCOCH3, this CC bond will be broken and there will be CN double bond formation, and ultimately there will be removal of OAC. So this CN bond formation, as you can see, CN triple bond, positive charge is generated at this carbon, and finally this molecule, if you draw it in a different way, so that is equivalent sign, I have drawn it in a different way. So it is a 5-member ring, 1, 2, 3, 4, 5. Okay, so this is 1, 2, 3, 4, 5. So if you start 4 here, it will be 5 like this. Okay, so finally we are getting 5-member ring, and as we have a positive charge here, we will remove H plus from this position, and this double bond is stable also because this is substituted. So in this way you can see this total process, how you can describe it. It is fragmentation, and after fragmentation there is that is how the positive charge is generated. There is removal of proton. Remember in the first slide I have already shown you that this can be a fate of this positive charge after fragmentation. Nucleophilic attack, that is very common, that we have already seen some examples, but removal of proton is also possible, and after removal of proton we are getting alkyl CC double bond. So these are the examples of Beckmann fragmentation. I hope this video will be helpful to you. Thank you for your time.